quiz today. I'll give you probably 15 minutes towards the end of the class. A few questions regarding the semiconductor system, ecosystem, and also a very simple question regarding superposition. Connor is like, no. Okay, so we are going to design a DAC pretty soon, maybe starting next week. So let's look at the DAC circuit first. Okay, the DAC structure we are doing this time is called R2R. It's a resistor string. Oh, I can turn on the TV. And this is VL. These are the digital inputs of the DAC. And you put everything in one block. It's a DAC chip. Looks pretty simple. Right? So what are the possible values for D0 to D3? It's D0. There are digital inputs. It's 1 zeros, right? If you have 5 volts, this either 5 volts or ground. So you can consider these ones as a power supply. You can imagine there's a little power supply over there, right? Feeding a voltage to each of them, and it could be 5 volts or 0 volts. Okay, and so how do we solve VL? Depends on different inputs. The inputs can be, how many combinations can we have for this circuit? How many different inputs? 16, 2 to the 4th, right? 16 inputs. So there are 16 inputs, and we need to find out an equation to calculate VL. There are so many possibilities. So how do we derive the circuit? So I have to use superposition and Thevenin's equivalent. Okay, so for here, if we just do D1, the first case, if D0 is VDD or 5 volts or logic 1, and D1 equals D2 equals D3, D3, they are all 0 volts or ground, and it becomes, you know, just the 5 volts here, but all ground for the other 3 inputs. And this circuit becomes a, if we draw an equivalent circuit to this part, just this part, because we got a 5 volts here for D0. Okay, if we draw it, it becomes this. See if this makes sense to you. And what is the output over here? What is the load in this circuit? No. Because we are trying to find an equivalent circuit from here to here, right? And yeah, can you imagine that we consider this point. So this point becomes this output node, and this point becomes here. So for here, you just rotate it, right? And then you rotate everything here behind this resistor, behind this node, and you put it here, right, as output or load the circuit here for the first one, for the first part. That makes sense? Okay. And can we find out the equivalent of VTH and RTH for this part? Quickly. How do we do it? So we short the power supply, and looking backwards. So it becomes this, right? 2R, 2R. And because they are both grounded, so you can short them together. Right? So you are looking backwards like this. Current flows through in that way to get two branches. To have two branches that merge together. Okay, so what is RTH? 1R. Does that make sense? So for this very simple voltage divider, RTH equals 1R. So what is VTH? VTH is voltage at the output node. So what's VTH? Yeah, half VDD, right? So eventually this part can be converted into something like this. Yeah, that's a resulting equivalent or a Thevenin's equivalent circuit, right? So here's VTH, here's RTH. So VTH is VDD over 2, and RTH becomes R. So this equivalent circuit is whatever here. So you can replace this part with this one. Does that make sense? So the final circuit becomes so we just connect this point to here, right? And get another R, which is this R. We just put it in there. And then just copy the following. What's the voltage here again? Yeah, 2.5 in this case. Okay. So what are the D's here individually? So it's D1, D2, D3. These ones, right? And these two resistors are in series. So it becomes one resistor, which is 2R. Okay, by doing one Thevenin's equivalent, you get rid of D0, and you got another circuit very similar to the one over here. You just reduce 4 bits into 3 bits. And you can simplify this further. Let's do it one more time, a few more times. Eventually we can find out VL. So for this one here, we consider this part as a voltage divider circuit. And now we treat that D1 is also 1. That's the only way that I can consider D1 is contributing to the VL, right? So what we are doing here, we are considering an example which is 1, 1, 1, 1 as the input. Otherwise, we just ignore D1. We don't need to deal with it. So just in case, D1 is 0, what's going to happen? If D1 is 0, what's going to happen here? Do we need to do anything? So, and one more question before I answer that question. Okay, so we move the circuit from here to here. We are treating D0 as 100. 1. If it's 0, then we just directly find it becomes a parallel resistor, it's just 1R. We're not getting any half VDD here, right? So it was a 1. So in this case, we are having 1, 1, 1, 1 for this as an input for the DAC. Okay, just keep in mind. And the circuit becomes this now. If we have 1, 1, 1, 1 as an input to the DAC, okay. So now we are trying to find the contribution of D1 to VL. Here's still VL. So if we are trying to find out D1's contribution to VL, we should only have D1 being effective, but all the other sources should be shorted to ground. Is that true? Okay, so the second case is if the let me see. If D1 is 5 volts or is VDD, and this circuit becomes this. No. This part, we short this to ground and only D1, so we got a resistor. So this is D1, which is VDD at the very beginning. And this is output node. And this is whatever the circuit we want to treat as a load over here. Okay. The same way, and eventually you are getting a, wait, let me see if I'm doing this right. I think I want to use 0 for D1, D2, D3. But only D0 is 1. Instead of having all of them to be 1s. So it's easier to calculate the results. Sorry about the error here. So in that case, if D1 is 0, okay, that makes a lot of sense. If D1 is 0 in this case, we move this half VDD to here. All right, and the rest circuit here is the load. So what's the 7 is equivalent for this part? Let's calculate one bit at once. Okay, don't do all the ones at one time. It's getting more complicated. Hoping I'm not confusing you. Just too many things can change. Is that making sense to you guys? Not really. So we changed the input from 111 to 1000. Okay, let's do one at a time. I don't want to make it too complicated. Right? And from here to here, it makes sense, right? Mm-hmm. It's a voltage source, and we treat the rest of the circuit as a load. Okay, just whatever. It's just in the black box. We don't care what is in there. Right? And this part is definitely 5 volts because this is the logic 1. So 5 volts with one resistor here, another one here connect to the ground, one here, another one connect to the ground. Okay, so this is the voltage divider, and this is the output nodes. Okay, and this is the load. Because VL also has a ground. VL is compared to the ground is V out. Okay, so they have a common ground. Now don't worry about that for now. So whatever here is just a load. Okay. So that's how we got this circuit, and we convert it into the 7 is equivalent, which is this half VDD connect be in series with R. So we replace this part with the equivalent 7 is equivalent. So we got this. We got 2 R's in series, so it becomes 2R. All right, and we are having all zeros for D1, D2, and D3 right now for this example make it easier to calculate. Yeah, eventually later, yeah. But right now we are just working on V1 only, right? So that's why all the other voltages are zero. It takes time to get all of them done. So now we're just doing one. Yeah. Yeah. Good question. So in the future, right, if you got a different input, you have to do the whole process that I'm working on right now for each bit. For each one which has a 1 on it. Okay. Now let's just do one first. You'll get there pretty soon. I have a quiz on it. I have a few homework assignments on it. Okay. It's getting easier because right now we just reduced the one voltage input, right? Now we have a half VDD connected to 2R and a 2R here, and this is 0, which means it's a ground, right? So we just treat this one as a load, as a black box, this part as a black box, and this is as an output of the node of the circuit here, and this one connects to the load, right? So what's the voltage here? It's easier to calculate because you got a VDD over 2 and you got a voltage divider, so the voltage here becomes but we still have to convert here into its Thevenin's equivalent. Okay, now let's do it. So this part, if you convert, if you find its Thevenin's equivalent, it becomes similar as the first one we did, right? You got RTH, which is, yeah. And VTH is this one divided by 2. It becomes VDD over 4, right? Is that correct? And then we replace this part with the Thevenin's equivalent. And now we are getting VDD over 4 Okay, and this becomes 1 2R here. And we find Thevenin's equivalent here again, which becomes VDD over 8. Here's still VL. You learned Thevenin's equivalent in circuit 1, but you never saw it's that useful, right? So what is VL? If we only have D0 to be 1, but all the rest digits or input digits are zeros, okay? So which means we're inputting a digital number of what? So D input is what? It's a 4-bit digital number as an input to the DAC. So what's the digital number? What's the digital input? If I have only D0 to be 1, all the rest are zeros, what's the digital number here? So if we have D0 to be 1, but all the rest of the digits are zeros, what is the digital input to the DAC? No, I mean just for now, okay? So DAC is, you got a digital input, 4-bit, it's a 4-bit DAC, right? You got a 4-bit digital input, you got a VL. Make sense? It's a DAC. You got a 4-bit input as a digital number, which is here. And then you got a 1 analog number, which is VL. It's a DAC. This is a DAC, even though it looks super simple, it's a DAC, right? It's R2R DAC. So you got a 4-bit digital input, you got an analog one, it's just one output. It's an analog output, like the picture or the block I drew on Wednesday, remember? You got multiple inputs and only one output as an analog output. Here's the analog output. Here's the digital input. So what is the digital input in this case? No, it's 0, 0, 0, 1.
So D0 is
it's the LSB. Now it makes sense because what is VL right now? What is VL? We are already at the final stage. It's almost done, right? We did all the 7 is equivalent. Then we are arriving at here. So what's VL? Yeah. 1/16 of VDD, right? Is that 1 LSB? It is. You have VDD over 2 to the nth, right? So just verify that this digit only contributes this much of VDD to VL, right? And you want to see if D1 is contributing 1/8 of VDD. Let's see if that's the case for D1. I'll do it real quick. We want to run all the process. But I can tell, right? If you have you're just being divided for more times, right? If you have a 1, so for example, if we start with D1, it's gonna start from here, right? Instead of having a half VDD, we have a VDD because that's a D1 as 1 VDD. Yeah, let me show you. If D0 is 0 and only D1 is 1, right? So this is D1. So now D1 is 1. But all the rest are zeros. Where should you start? Get started with this circuit to find out VL. What's the first step? What is the first step to solve it? It's just a parallel resistor, right? Merge. What's the result? 1R. So this becomes 1R. This is R, right? And this is 1, this is ground, this is ground, this is 2R, 2R, R, R, 2R. And this is 2R, right? 2R. What's next? Just do whatever we just did, right? Just follow all the steps. But instead of here being a half VDD, now we have 1 VDD here, right? Start with 1 VDD, that's why eventually you are getting VL as what? Yeah. Okay. So what if we have D3 to be 1? So if D3 to be 1, you can imagine you can merge, or you can just simplify the circuit as, so since all these are grounds, right? All these are grounds, so you can keep merging all these resistors. You got a R, you merge, you got 1R and 2R, right? 2R got a 2R here, and 1R, okay? And 2R, and 1R, and 2R. And eventually it becomes these 3 So if you only have D3 as a 1, but all the rest are zeros, you just combine all the resistors and eventually you're getting this circuit. So VL is a half, right? So in that case, D equals D3, D2, D1, D0, which is what for this case? Wait, the digital input, right? Is that a half? Yes. So I have 16 in total, and this is 8. So that's why it's, oh, sorry. So half VGD. Remember how to calculate the VL for the DAC? It's a digital input, which is the digital input word. The input word. This is called the input word, which is 0011000 over the total number of combinations for that DAC, right? And times what? VREF. And VREF here is 5 volts. So it becomes 1000 over 2 to the nth, which is 8 over 16 times 5 volts, which is a half VDD, which is 2.5 volts. So if you have D3 to be 1, it's outputting 2.5. Any questions by far? Are good on it? So if I give you another random input word, are you able to solve it? So now we already calculated 1, 0, 1, 0, 0, 0, and 1 and 0, 0, 0, 1. Okay. So if the input is 1, 0, 0, 1, what's VL? What is VL? If the input is 1, 0, 0, 1, okay, like 1, 0, 0, 1. Yeah. 1/16 plus 8/16, right? Good. What about other numbers? If I have some ones in the middle, it's still doable. Just do each one at a time, right? Just have that one as 1, but all the rest are zeros. Okay. Because if you have the 1 here, for example, all the rest are zeros. You can just start combining all the resistors and eventually getting a 2R here, 2R, 2R, right? And you can start from that digit to do the 7th equivalent. It's gonna be on the quiz. I'm gonna give you random digital inputs to ask you derive, or find out VL using superposition and 7th equivalent. It's fair? Is that boring? Makes sense?
Like I didn't know where the equation came from the last lecture.
Okay. Van, have any questions? Yeah, but it's recorded, so you can review it later, okay? Make sure I understand it, important, okay? Since we are building this DAC, I think as a course project as well, it's gonna be everywhere in the semester. I also have to review op-amps for you guys because it will be part of the ADC, not DAC, ADC. If you are building an ADC, we need a DAC in it. I'll show you. So that's a schematic of the ADC we built a few years ago. So it has a sample and hold circuit. We're going to get into that as well. A comparator, which is the op-amp. That's why we have to talk about op-amp. today. And this is a, what is this? Oh, this is a SAR registers. I'm gonna go, teach you how to understand this as well. Pretty interesting circuit. And that's the R2R DAC. Okay. I'll learn how this works later and why we need a DAC here. So that's the digital output, input from the register array, and send the signal back to the comparator and then feed into the SAR register. And you'll understand what's going on in the circuit later. Okay, all right, about that. So just want to show you that here is the comparator we have to use. It's just a regular op-amp, and we should review the comparator here so you know why we need a comparator for the circuit. So when we talk about comparators, we have to talk about op-amps. Operational amplifiers. So VL equals what? For example, this is VP, this is VM. Just to remember, if you grab an op-amp from the lab in the drawer, right, it has a ground pin and power supply, just power it up and ground it. Don't connect any resistors or feedback circuits to the inputs now, right? Just power it up and ground it. So what is VL? VL equals VP minus VM times AOL. AOL is the open loop gain. What is the value, a common value for the open loop gain for the op-amp? No, open loop gain is usually huge. Let's treat it as, for example, 1 million for now. And it's designed in that purpose. They designed it to be 1 million or sometimes 100 million. Ideally, it should be infinity, but let's treat it as 1 million for now because it's a huge value. And we don't have to worry about the design details of the op-amp since we are not designing op-amp. It's just the properties you need to know. Like you buy a car, you need to know you can drive the car, right? The car has a audio system as well. You just need to use it. You don't need to design the details as of now, right? So if you grab op-amp, how to use it? This is what's happening. If you grab a component in the drawer in the lab, you should know that VP minus VM times AOL becomes VL. It can be really confusing, okay? And also in the interviews, people may have some of the op-amp questions in the interview. It's confused so many people. A lot of times, 90% of the electrical engineer graduates, they don't know how to answer questions in op-amp related topics. It can be very confusing because I've been using the black box all the time. It just takes so long to learn how to design the op-amp, and we don't have the time to cover it. So instead of doing that in the end of the courses, as a first microelectronics course, like the analog circuits or any other the circuit one, we don't have time to cover the details. We just teach you guys how to use it. It's very easy to forget, the properties and how to what's going on with the op-amp. So why do we need that? If we connect, for example, VP to a reference voltage like 2.5 volts, and we power it up at 5 volts, and the input is a varying signal. So this is the total range here, which is 5 volts, and we get 2.5 volts as a reference voltage. And VP minus VM, for example, if I have this is VP, okay, this is VP. And if VM is changing this way, what VL looks like. This is 1 million or infinity, for example. So VP minus VM if VM is smaller than VP, so this is VM, in this period or before this time point, which one is larger? VP or VM is larger here. VP is larger, right? And VP minus VM can be any of the values, all the differences over here. But times a million, it just becomes a huge number. And it's going to saturate the op-amp output and becomes 5 volts. It could be, even though there's a very small change, okay, even VP is just slightly larger than VM, it's going to saturate the output very quickly because it's trying to give you a like 1 million volts, but it only have 5 volts as a power supply, so it's not able to supply that million volts. It's going to saturate at 5 volts. That's what's going to happen. So what you are getting during this period will be what? 5 volts. Okay. But when the VM is getting larger and larger, getting close to VP, the output becomes 0 because VP minus VM is 0. 0 times whatever is 0. So it drops to 0 at this point. And during this period here, VM is always larger than VP, right? VM is always larger than VP. VP is just a straight line, 2.5 volts. So VM is always larger than VP. VM is larger than VP, right? And it's going to give you a negative number here, and the negative voltage times a gain, it will just be more negative, like negative 1 million volts or something, but it's not able to supply that voltage. The lowest voltage in the circuit is what? The lowest voltage the circuit can supply is ground, which is 0 volts. So it's going to saturate at 0 volts. So in this period, it's going to be 0. And during this period, VM is lower than VP again. So it's going to jump to 5 volts and keep it until here and then come back. You got a square wave, right? So what's the square wave here? What is the signal in this circuit? Just make sure you guys are still, on your toes. So what is this square wave? VP or VM? VL. So it's a comparator. It's comparing input and output and giving you a 1 or 0. Depends on which one is larger or smaller. Just comparing and giving you a, it's making sense because you need a digital signal. It's 1 or 0 to know which one is larger, like a yes or no. So next, probably on Monday, I'm gonna talk more about the why do we use the negative feedback in the op-amp in addition to just the comparator, or if I just swap the signals. So this one VM is now the reference, and VP is a varying signal here, and this is VL. It's also 5 volts and ground. So VM, yeah, that's right, 2.5 volts for VM, and VP is varying. This is VP, 2.5 volts. Varying, sorry, VM is VM, 2.5 volts, and this is VP. Can we draw VL in this circuit? This is VP. Let's start with this part first. So VP is smaller than VM. Look at this equation. VP is smaller than VM. You're getting what for the VL? 0. When VP is larger than VM, you're going to positive number here times a gain, huge gain. It becomes a huge voltage, but the supply voltage, the voltage supply cannot supply it. So it becomes 5 volts. It's going to saturate at 5 volts. All right. Any questions on this so far? We're good? Okay. Let's do our quiz. Talk more about it next